Let's look at limits at infinity. All right, so the end behavior. We've been talking about end behavior since like the first month of school, all right? So the end behavior of functions can be discussed in terms of limits at infinity. They're basically the same thing, but the notation's different. So instead of end behavior notation like as x approaches infinity, blah, 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 we put the limit as x approaches infinity and whatnot. So recognizing the end behavior that we already know in behavior patterns of power of polynomial and rational functions can help identify limits at infinity without graphing the function. Like we don't have to look at a graph because there's things we already know about a graph. Okay, so let's think about what we know about power functions. So given the power function f of x equals x to the n power, when n is a positive integer, the following limits are defined as blank. All right, so if n is even, well, we already know, the way we looked at n behaviors, that if we knew that n was even, if it's a power function, it looks like this. But if we're just talking an even polynomial, then we knew that it looked like this, right? Up was like our end behavior. That's what's happening there. And so as the limit, as x approaches negative infinity, so as x gets smaller and smaller and smaller, y is approaching infinity. It's the end behavior, just like we looked at before. The limit as x approaches infinity of f of x, and by the way, this notation is important too. Most of you did that beautifully when you were writing it out. Some of you made up your own thing and you're not allowed to do that. Okay? The limit as x approaches infinity of f of x equals, so as we're going to infinity, this should be infinity. Also for my students that when we're doing Go Formative, I was very clear on my instructions on Tuesday and Wednesday. I believe I said it in at least one of the videos, and I know it was written both days. These are to be written, not typed, because you're not typing them right anyway. Written, which means you have to actually write on a touch screen. Like, welcome to 2021, right? All right, so n is odd. So in behavior, down, up. So the limit as x approaches negative infinity, f of x approaches negative infinity. The limit as x approaches infinity, f of x approaches infinity. Okay, we good? You writing with your mouse? You're talented. Okay, so let's talk about the polynomial functions. So these were just like simple little power functions. But when we look at the polynomial functions, polynomial looks like this crazy long thing, right? So if I want the limit as x approaches negative infinity of this whole polynomial, I don't have to worry about the whole thing. It's the exact same thing as the limit, make sure you're writing this notation correctly, as x approaches negative infinity, right? That goes right underneath the limit. Instead of the entire thing, we only have to worry about that first term, so that's a sub n times x to the nth power. That's just your leading term, that's all that means. And the limit is that as x approaches infinity of the entire polynomial is the same as the limit as x approaches infinity of just the first term, which is a sub n times x to the nth power. Easy enough? So you just have to look at this. So basically you get to treat it like a power function. That's all it's saying. So this means the end behavior of a polynomial function, can be described as the end behavior of its leading or highest degree term. Because it's not always the first one, it's the one that should be the first one with the highest power. Okay, so let's look at this. I have the limit as x approaches negative infinity of all of this stuff. Notation and format is so very important. You cannot be sloppy with this stuff just because you're getting to do a lot of stuff digitally. Like you're just going to get hammered in calculus if you're not doing this correct. So make sure you're paying attention to this because it's not that hard. You just have to know that it's important. If it wasn't, I wouldn't make you write it because what's the point? This is equal to the limit as x approaches negative infinity, right? That's how we write it, of just the leading term, or the one with the highest power. That would be x to the 4th power. Now, the limit of that is going to be just a number or infinity. It's not an f of x equals, it's not the limit equals. Like, once we evaluate it, then the limit part of that goes away because there's my answer. So if I look at this, this is a positive even function, so my end behavior looks like this. It's up, up. So as x approaches negative infinity, what does x to the 4th approach? Infinity. So my answer is infinity. And that's it. Okay, easy enough? All right, so let's look at number 2. So the limit as x approaches infinity of this polynomial is equal to the limit as x approaches infinity of which term? Good, negative x cubed, yes, negative x to the 3rd. So I know that end behavior for an odd is down, up, but this is negative, so this is what my end behavior looks like, right? So then as x approaches infinity, this function's going to approach negative infinity. So this is the end behavior. We don't care about what goes on in the middle, because this isn't going to look just like a regular old cubic function, and this isn't going to look just like a regular old quartic function. There's other stuff going on in the middle. Remember when we sketched those and we found where it crossed and if it was a bounce and all that kind of stuff? But that's irrelevant when you're talking end behavior. That's all middle behavior, and that's for something else. Okay, we good so far? All right, let's jump to number 5. So I've got the limit as x approaches negative infinity of which term? Good, negative 8 to the 6th. Negative 8x to the 6th. All right, and so this is negative, and it's even, so this is going to be down, down, which means as we approach negative infinity, it approaches negative infinity. Just FYI, another way to do this, because I think Delta Math might do them this way, this is the same thing as, just like I said, to me at this point, I think it's easier for us to do it this way, but if you see Delta Math explanations this way, I want you to know that it's the same thing. It's not that, you didn't learn it right or anything. You can technically factor this out, so we can make this like negative 8 times the limit as x approaches negative infinity of x to the 6th power, like that. So that would mean since x to the 6th is even, as we go to negative infinity, we go to infinity. But then when you multiply that by a negative 8, it makes it negative infinity. You get the exact same answer. And I just don't think that's necessary at this point, like the level we're at with limits. So it's fine to do it this way. I'm just telling you that because I know when you get things wrong in Delta Math, it shows you an explanation. And I don't want that to become a source of confusion. It really doesn't matter which way you do it. It's fine either way. All right, so you write out all this stuff for number 6. Give you a second, and you just do number 6 on your own. I like your crayon. Is it easy? Is it easier than a stylus? Yeah. It is a stylus. Well, I know, but I mean, like, it's like just like a regular. It's more bubbly than that. So it's just easier to control and stuff. So this is what I got for number 6. I got negative infinity. We agree with that? Because this is odd, so instead of being down, up, and it's negative, it becomes up, down, and there's your answer. Okay, so it's literally the same in behavior that we've been looking at before. The notation is just a little bit different. Same concepts, though. Okay, just kind of move it into something else. All right, so let's look at rational functions. It says the following rules can help us find limits of rational functions at infinity. So let's look just at reciprocal functions, meaning we only have variables in the denominator. So if I only have variables in the denominator, this is what it looks like if it's 1 over x, and this is what it looks like if it's 1 over x to the nth. It says where n is a positive integer, and that's true, but this also needs to be an even integer. An even positive integer. All right. So this is one where it was similar to this on the assignment, where a lot of people miss this one because they put the limit as x, it said in behavior, it said limit as x approaches 0 and it doesn't exist. Now, that's a true statement, but it has nothing to do with the in behavior. In behavior is out here. In behavior is approaching infinities. We don't care about middle behavior. Middle behavior is irrelevant at this point. All we care about is the limit as x approaches negative infinity, so as x gets smaller and smaller and smaller, what is y approaching? 0, because there's an asymptote there, right? And the limit as x approaches infinity is also going to be 0. Here, the limit as x approaches negative infinity, still approaching that 0, and infinity, still approaching 0. On this one, it's approaching from below instead of above, but they're still approaching 0. The limits are all the same. So we can use that concept, but we're also going to use some direct substitution with infinity, because that's another concept that you need to be able to think through. So let's look at this one where we want the limit as x approaches infinity of 1 over x to the 4th minus 7. So we're going to take this as, we're going to substitute in. And when we evaluate, we're going to evaluate by direct substitution. Means when we evaluate it, the limit part of that drops off because we are finding the limit. So this is going to become 1 over, I'm going to substitute it in that infinity, infinity to the 4th power minus 7. All right, well, infinity to the 4th power is infinity. So I need to think about what 1 over infinity is, or what is it approaching, because we're talking limits anyway. And then for a fraction, when the denominator gets bigger and bigger and bigger, what happens to the value of the fraction? It gets smaller and smaller and smaller, right? So if this denominator is going to reach infinity, that means this number is getting minutely as small as it possibly can, which means this is actually approaching 0. Does that make sense? So that means that this is actually 0 minus 7, which is 0. And that's my answer. So 1 over x to the 4th doesn't actually equal 0, but it approaches 0, so we can talk about it like that because we're looking at limits, all right? I could think about it this way. Like if I had ignored this negative 7, 1 over x to the 4th is going to be like this right here. So my limits are 0. But I've shifted down 7, so my asymptote goes from 0 to negative 7. That make sense? Oh, I don't know why I wrote 0. I don't know why I wrote 0. Oh my gosh. Thank you. 0 minus 7 is not 0, guys. What is it? Negative 7. Good Lord. I don't know. I think my brain was jumping ahead to the... because it has shifted down, and that's where my asymptote is. Thank you for asking. Anything else? I wanted to see if y'all were paying attention. Good job. Yeah, you don't really need to, but you can. All right, let's see. So I'm going to evaluate this one as well. So we're going to go ahead and substitute with this one. So this is going to give me 5 over infinity squared plus 1 over infinity. Oh, negative infinity squared. Good Lord. All right, so in negative infinity squared is infinity. All right? Infinity to the 50th power is still infinity. Infinity is a fascinating thing. But, so either way, what's the value of this fraction approaching? 0, right? So this is going to give me 0 plus This one also is approaching 0. It's just approaching 0 from the other side. So it's 0 plus 0, and your answer is 0. Okay. Everybody good so far? All right. So then it says, given the rational function, by dividing both the numerator and denominator by the highest power of x that appears in the denominator, we can use the polynomial and reciprocal rules to evaluate the limits at infinity. Because direct substitution here, not going to work, because you're going to get infinities over infinities, and is infinity less than infinity squared? No, it's not, and that gets all weird and just, no, it doesn't work anymore. So instead, at first, this is going to look very strange, and it's going to look complicated. It's really not. It's just some weird stuff that we have to write. So it says to take the highest power of x that appears in the denominator. So that would be x cubed. So we're going to rewrite this. This is still the limit as x approaches negative infinity. And we're going to divide every single term by x cubed. So this is going to give me 6x squared over x cubed plus 2x over x cubed. Then I'll get 2x cubed over x cubed plus 3 over x cubed. Okay, everybody with me so far? Then all I'm going to do is simplify that. I'm not evaluating yet, so I can't drop my limit off yet. So then this is the limit as x approaches negative infinity. So 6x squared over x cubed is going to be 6 over x plus, this will give me 2 over x squared. Then the denominator, I'll get 2 plus 3 over x cubed. Okay, so all I did was simplify what was in that fraction. Does that make sense? Good? All right, so now that I've done that, now I can do some direct substitution. And so even though I'm going to do the direct substitution, I'm not going to write the infinities anymore. I just wanted to make sure you got the idea. So if I substitute in negative infinity here, the value of this fraction is going to approach 0. Plus 2 over negative infinity squared, that's also going to approach 0. In the denominator, I will have 2 plus what? 0. So that gives me 0 over 2, which is 0. That one really is 0. Everybody good so far? Because if we had just substituted in infinities, I'd have had infinity squared over infinity cubed, and it just doesn't work that way. That doesn't equal 0 or anything like that. We good? All right, so let's do the same thing on number 10. So this is going to give me the limit as x approaches infinity. And so I take the highest in the denominator, which is x squared. So this is going to give me 5x to the 4th over x squared over, then x squared over x squared plus 2 over x squared. Then I'm going to simplify. So I still have my limit as x approaches infinity. Numerator is going to give me 5x squared. Then this will give me 1 plus 2 over x squared. Okay. Now that I have it simplified, now I can do my direct substitution again. When I substitute infinity into here, 5 times infinity squared is just infinity over 1 plus 0. So that'll give me infinity over 1, which is just infinity. Any questions at this point? All good. I'll give you enough time to write. Okay. All right, so let's look at 11. Highest exponent in the denominator is x. So you go ahead and work through this one without me talking you through it. So did we at least get to this part of the simplified limit, right? So then when I substitute in my infinity, this is going to give me 2 minus 0 over 8 plus 0. And then that's just going to reduce to 1/4. So let's take what we know about rationals. We graphed rationals. We did all kinds of things with rationals. And one of the things that most of our rationals had were horizontal asymptotes, right, of some sort. And so let's think about what that means. If I was going to look at number 11 and say, all right, well, remember how we talked about top heavy, bottom heavy, tied in degree? So since these both have x to the first, this one is tied in degree. And your rule for when they are tied in degree to find that horizontal asymptote, it's just the ratio of the leading coefficients, which is 1/4. Remember that? Then let's look back at the last ones we just did here. Let's look at number 10. So this one, x to the 4th and x squared, so this one is top heavy. Your rule for top heavy was none, right? Didn't have one. And it doesn't because it goes to infinity. The horizontal asymptotes are going to stop it from going to infinity, so there is none. And then this one here, we look at these two, this one is bottom heavy. And your rule for bottom heavy was that your asymptote is at y equals 0. So this is the algebraic way to find them. It is a process that you need to have seen. That's why we did it, not just for me to torture you. But you need to know that this process exists. It's something that you are going to look at. But because we know some rational rules, we can actually skip doing all of this work. Okay, so I wanted you to see how to get it with all of the work, because again, it's a process you need to be familiar with. But to do the last ones, we can talk about some rules here. So it says, looking at the examples above, notice that the limits of rational functions at infinity follow their horizontal asymptotes. So we can generalize things. If you have a rational function and the degree of p is less than the degree of q, so that means that makes this bottom heavy. Bottom heavy for a rational means that your asymptote is at y equals 0. So then, therefore, the limit at plus and minus infinity, since you've got this y equals 0 here, is 0. It's not y equals 0 because that's the asymptote, but the limit is 0. It's the same. Okay? And then if the degree of p is greater than the degree of q, that makes it top heavy. That meant we didn't have an asymptote. So if I don't have an asymptote, if I don't have something stopping it, then the limit is plus or minus infinity, depending on the function. And then if the degree of p equals the degree of q, that means that they are tied in degree. Then the limit is the ratio of the leading coefficients. It's the exact same rules as your asymptotes for rationals. So that's how we're going to work these last three. We could do the whole dividing thing like we did before, but instead, we're going to look just at the leading terms. So I'm going to rewrite this as the limit as x approaches infinity of 2x over x to the fourth. So when I look at that one, that is bottom heavy. Since it is bottom heavy, I have an asymptote at y equals 0, which means my limit is 0, and I do not have to divide and make those weird looking fractions. Easy enough? Okay, so let's look at number 13. This is equal to the limit as x approaches, that does say negative infinity, right? Mine's all blurry. Okay, thank you. It's just like a blob up here. So the leading one in the numerator is 10x cubed over, in the denominator that's a negative 2x cubed. So here I am tied in degree. So since I am tied in degree, I take the ratio of those leading coefficients, and my answer is negative 5. That's where my asymptote is. And that's what gives me, my horizontal asymptote. That's what tells me about end behavior. Okay? So then here, I'm going to have the limit as x approaches infinity of negative x cubed over 2x squared. So this is top heavy, which means there's no asymptote. So my answer is either plus or minus infinity, and I have to figure out which one it is. So I'm going to take this infinity, and I substitute it in just in the numerator. So infinity to the third power is infinity, but then I have to make it negative, which makes it negative infinity. Had this been negative infinity, like had this said x approaches negative infinity, when I substitute that in here, negative infinity cubed is going to be negative infinity, right? And then I make it negative, so my answer would be positive, all right? This is another one where Delta Math may show you, it may show you to factor out that negative, and say, okay, this is negative of the limit as x approaches infinity of x cubed over 2x squared. You're going to get the exact same answer because you're going to say, all right, well, I'm going to take infinity, put it in here, that gives me infinity. So my limit is infinity, but then I have to make it negative, so my answer is negative infinity. It's however you choose to think about it, but I want you to see that. I would just say it's easier just to handle it this way at this point, but because you may be shown this, I just want you to know it's the same thing, okay? What questions do we have? Anything at all? We're all good? All right, your assignment is in Delta Math today.